Now we will find various methods to evaluate the residues of a function f of z. Now we take f of z is an analytic function and we will find the residues of f of z at the singularities. The first thing that we have to make note is that your function f of z should have singularities, and if it has singularities you have to verify whether it is a simple pole. Simple pole implies z is equal to a should be a root of the denominator and that should be of order 1. If it is a simple pole, then the formula to evaluate the residue is this. Residue of f of z at z is equal to a is limit z tending to a z minus a into f of z. If it is a pole of order m, that is z is equal to a gets repeated m times, then the residue is calculated using the formula 1 by factorial m minus 1 limit z tending to a d power m minus 1 by dz power m minus 1 into z minus a whole power m into f of z. In other words, you have to differentiate z minus a whole power m into f of z m minus 1 times and allow limit z tending to a and multiply the resultant with 1 by factorial m minus 1. So now here we have three problems and we have to calculate the residues of these three problems. So now when you move to the first problem, f of z is taken as z cube minus z squared plus z minus 1 by z into z squared plus 4. Equate the denominator to 0. Z into z squared plus 4 is equal to 0. So z is equal to 0 and z is equal to plus or minus 2y. Z is equal to 0 gets repeated once. Z is equal to 2y and z is equal to minus 2y also gets repeated once. So the three singularities are simple. So now to calculate the residue at z is equal to 0, I have to multiply f of z with z minus 0, which is z, and allow z tending to 0. When I do it, the z in the numerator and z in the denominator gets cancelled, and when I allow the limit z tending to 0, I will have minus 1 by 4. For the second pole, z is equal to 2y, I have to multiply f of z with z minus 2y and allow z tending to 2y. And when I do it, z minus 2y gets cancelled. And now when I allow z tending to 2y, I get the value as 6i minus 3 whole divided by 8. Now for the third singularity, I have to multiply f of z with z plus 2y and allow z tending to minus 2y. Already we have classified z is equal to 0, z is equal to 2y, z is equal to minus 2y are simple poles. So when I multiply f of z with z plus 2y, z plus 2y gets cancelled in the numerator and denominator, and when I allow z tending to minus 2y, I get the residue as 6i plus 3 whole divided by minus 8. So this is a problem where all the three singularities are simple. Now you consider this function f of z is equal to z plus 1 by z minus 1 the whole squared into z plus 3. Now what I have to do is I have to calculate the singularities. To calculate the singularities, what I do is I take the denominator to be 0. So z is equal to 1, that gets repeated 2 times, and then z is equal to minus 3 is a simple pole. So when z is equal to minus 3, I apply the formula that has been applied for the first part of this problem. And for z is equal to 1, I have to use the second formula for finding the residues by substituting m is equal to 2, because that gets repeated 2 times. So first we classify that z is equal to minus 3 is a simple pole and z is equal to 1 is a pole of order 2. And as usual, to evaluate the residue at z is equal to minus 3, I multiply f of z with z plus 3, and z plus 3 gets cancelled in the numerator as well as in the denominator, and that gives you 1. Okay, in fact here it has to be limit z tending to 3, is right. So I'll have 3 plus 1 4 by 4, which will give you 1. Okay, so in this case residue at z is equal to minus 3 is 1. Now what I have to do is I have to calculate the residue at z is equal to 1. Z is equal to 1 is a pole of order 2. So I substitute m is equal to 1 in the formula. So d power m minus 1 by dz power m minus 1 will become d by dz. Multiply f of z with z minus 1 the whole square. Allow z tending to 1 and multiply this entire term with 1 by factorial m minus 1, which is 1 by factorial m. So in this case z minus 1 whole square gets cancelled. I have to differentiate z plus 1 by z plus 3 once and then allow z tending to 1, which turns out to be 1 by 60. So residue of f of z at z is equal to 1 is 1 divided by 60. Now for the third part, when you equate the denominator to 0, you get z is equal to 1. Z is equal to minus 3i and z is equal to 3i. These three are simple poles. So now what you do is you evaluate the residue of f of z at z is equal to 1. It has to be limit z tending to 1, not z minus 3, z minus 1 into f of z. So z minus 1 into f of z, this will be z minus 1 into 3z squared plus 2 whole divided by z minus 1 into z squared plus 9, and here z plus 1 gets cancelled here. Sorry, z minus 1 gets cancelled here. This will give you 3z squared plus 2 by z squared plus 9, which turns out to be 5 by 10, which is equal to 1 by 2. So the residue at z is equal to 1 is 1 by 2. Yes, you keep in mind that here I have made an error. It has to be z minus 1, not z minus 3. when I calculate here z minus 1 into f of z, I get the value of the residue of f of z at z is equal to 1 as 1 by 2. Similarly, when I calculate the residue at z is equal to 3i, I have to multiply f of z with z minus 3i. So here I get z minus 3i into f of z. This will be z minus 3i into f of z will be 3z squared plus 2 divided by z minus 1, okay, into z plus 3i into z minus 3i. Z minus 3i gets cancelled and that gives you 3z squared plus 2 by z minus 1 into z plus 3i. And when I allow z tending to 3i, I get 3 divided by 3 plus I. So the residue at the third point here will be like this. What I have to do is I have to multiply f of z with z plus 3i. So now how do you get this? Z plus 3i into f of z. This will be z plus 3i and f of z will be 3z squared plus 2 divided by z minus 1 into z minus 3i into z plus 3i. So z plus 3i gets cancelled here. So this gives you 3z squared plus 2 divided by z minus 1 into z minus 3i. And when I allow z tending to minus 3i, I get minus 3 divided by I minus 3. So now what we have done is we have evaluated the residues of certain functions. The evaluation of the residue depends upon the pole of order 1 or above. If it is of order 1 or simple pole, use the first formula, that is multiply f of z with z minus a and allow the limit z tending to a. If it is a pole of order m, then residue of f of z at z is equal to a will be 1 by factorial m minus 1 d power m minus 1 by dz power m minus 1 of z minus a whole power m into f of z. When you use these two formula, then you can find the residue of certain functions. So using the residues, you can find the value of an integral, okay, using the Cauchy residue theorem, which will be dealt later.